comfortable introducing yourself on the chat. And if you have any questions, you can go to slido.com and we'll be sharing information on how you can send out your question first. So let me pass it to Joki to introduce our presenter for this session.
All right, thank you so much, Mutiso. Okay, so like Mutiso said, this session will be led by Christopher. And as an R programmer, Chris works with a team of talented health economists at Oxford University to develop and apply innovative algorithms and scientific methods to process and extract knowledge and insights from healthcare data. Prior to joining Oxford, he worked as a clinical data manager at Cambridge Wellcome Trust for chain network study. This was a multi-country cohort with 9 sites across Africa and East Asia. Chris has a long-run experience in research data management and analysis with over 6 years of handling clinical trial data, as well as epidemiological observational studies. His interests include visualization of spatial data, predictive modeling, data mining, joint modeling, survival analysis, time series analysis, and general statistical computing using R. Chris will be training us on data management in R. In almost every industry these days, huge volume of data is generated at high velocity, and data is without dispute the main building block for scientific inquiry, decision-making, and project design. And as such, efficient data management practices become as critical as generating processes in order to benefit in getting useful insights. Data management is a combination of activities and processes applied to the raw data by means of processing, curating, and archiving the final clean, flat files for use in an analysis. In this talk, Chris will take us through step-by-step a process in managing and cleaning data using R language. He will also share tricks on how efficiently we deal with huge volume of data in the context of data management. Thank you so much for listening to me. And Chris, please go right ahead and have the floor. Thank you.
Well, thank you so much, John and Lucy, for that very elaborate introduction. And yeah, so if you allow me, I'm going to share my screen and talk a little bit. And if it's agreeable, I would prefer when I start the actual session for showing, doing the tutorial itself, I'll switch off my camera. That's if you don't mind. Okay.
Yes,
so,
okay.
Great. So are you able to see my screen?
Yes, we can.
Okay, so as if you heard, my name is Christopher Maronga, and I work as another programmer at Oxford University, NDORMS. This is a department dealing with the, it's an orthopedic department, so things to do with the osteoporosis and bone fracture and all those stuff. So yeah, so as Lucy has said, my main work involves using the R language to basically come up with innovative approaches and algorithms to process data and extract insights for the researchers to make decisions, or rather disseminate results. So, okay. So as part of the introduction, so you'll all agree with me that data is actually the most valuable component in any process that generates it. So be it in the financial industry, health sector, traffic, name them, social media, all the tech companies. So data itself, it's the core thing, like it's the core business of whatever you see around. So, and therefore managing it becomes a key interest to almost everyone. So, and therefore there are a wide variety of tools that are available to basically do that. And in this particular tutorial, I'm just going to use R to basically show you some of the workflows that you can basically utilize to manage your data. So in the context of data management, there are various steps. I know depending on what industry you come from, you can start talking of data management from like a point of view from if it's research. So we say data management starts from basically creating the data collection tools and creating the databases and validating all those particular warehouses where you're storing your data and all those stuff. But in this context, I am basically going to talk about one aspect of data management, which is collecting or processing. Of course, we have the collecting part of it. Then we have the collecting, the storaging, and the archiving. And basically, there are other issues, depending on which industry. We have the security, data security, curation, access, and sharing. So you're not going to cover those here. For this particular workshop today, we are going to basically focus on how can you process data. So the objective is basically to be able to take a data set and prepare it for a final analysis, statistical analysis in that manner. So yeah, and in this particular workshop, I will basically try to walk through how you can change the dimension of the data, how can you alter its structure, basically cleaning issues around data. And I make a very big assumption here that everyone is really familiar with the tidyverse, and at least you've used R before. And therefore, but if you are not familiar with the tidyverse, I'll try to, get you from that point to where we will be. Great.
Please, participants, please mute yourself as I'm fixing onto how I can mute all of you.
I have 3 themes today. That's manipulation, cleaning, and transforming. So under manipulation, we look at subsetting data and all those listed there. And cleaning will go around issues of missing values, root out improbable values. And basically we finish up with transformation, whereby now you're having to change the layout of the data from maybe wide to long, and do some group summary, manipulation, and all those stuff. So I'm going to stop sharing my video now, and I'm going to switch to my R studio, and we get coding now. But, a while back before this, so go to the layout, appearance, and just take the default one, then use that. That's fine. Okay. So I hope my screen is visible. Nothing is obstructing. Great. So
Is it
now
possible for you to zoom in, like for us to, it looks a little bit smaller from our end.
Okay, so you let me know when is that okay?
Yes, that's fine. Thank you.
That's fine. Okay, perfect. So now, so I'm going to use some 3 data sets here. So these are hypothetical, data sets depicting what actually happens in a normal, sorry, I don't know how to get this thing out here. So I don't know, need to put it somewhere. It's distracting me. Okay. Perfect. So just a minute. Perfect. Okay. So so a little bit of introduction to this data that I'm going to use. So there are this hypothetical research study with the baseline data, of course, discharge data, and a bit of follow-up data. So the idea is to emulate the different kinds of I mean, the different kinds of data scenarios that we encounter, long, wide, data collected over time, and how we can always process that to be able to have one flat file for appropriate for analysis. So, and as I said, we are going to basically focus on manipulating these particular data sets and trying to just get a taste of what actually what you can do with your data if you're thinking of preparing it for analysis. So, and just to remind you, the workshop is a beginner, so I mean I'm going to be as basic as possible so that everyone benefits. So I'm going to use these 4 packages here. I don't think I'm going to use anything outside this. So the tidyverse, as I said, if you're not familiar with the tidyverse, I mean, I have given some links on the slides, and you can always be able to read more about the tidyverse and what you can do with these packages. Perfect. So, so I'm going to walk you through what I prepared today. So, and just to read the data and load the packages. Yeah, so my first data set is the baseline, so which is containing a little bit few variables. That is the unique identifier of the patient, the time point, the date they were probably recruited to the study, the head circumference, weight in kilograms, height, age in months, gender, and all those other variables. Then I have the discharge data. So then a little bit of what this actually implies is that you find that in most longitudinal studies, especially the clinical trials or rather the observational studies, patients get, or rather research volunteers get enrolled into the study, then they get discharged, then they are followed up over time. So that's the scenario I'm trying to present here and how we can basically be able to collect this and process it in much finer details. The follow-up data is long format. I'm going to talk about the difference between long format and wide format. And actually, this was created by design so that we are able to take it back to the form that all of us will always want, so that you have all your data. You have a tidy data in the sense that you have all the rows represent observation. Each row represents observation, and each column represents a variable. Okay, so yeah, I already done that. The names of the function names, basically when you call it on a data set, it just prints to the console the names of the particular data set. And yeah, so I will jump in straight to the first theme, which is the data manipulation. And just going to remove this so that we can start afresh. Great. Okay, perfect. So, so first, we are going to look at subsetting data, and that is basically, selecting, dropping, or selecting variables. And in the tidyverse universe, we use the function select to basically either drop or retain the variables you want from your data set. So first, I'm going to just look at the general syntax of the select verb. Then later on, I'll introduce you to the mighty pipe operator, and we'll see how you can always combine some of these operations. So the syntax for select is just simple. So you call the function select. Then the first argument is the data that you want to select. Then from there you type in the names of the variables from your data set that you want to select, and you can end up like assigning that particular expression into an object. For instance, from my data set, I'm going to use the baseline data set. I'm just going to call the function head to just see the first few variables. So suppose I wanted to retain PID, that's the patient ID, date, height, and gender. So what I'll say is maybe I'll call it data frame 1. Then assign this to the function select, whereby I'm selecting from the baseline data. And what I'm selecting is the PID, height, probably, age, and gender, so like that. So when I run this function, or rather this particular call, I'll get data frame which is the same number of observation as the original one, but has fewer variables because I have decided to like the instructions was to retain those 4 variables. So I'll not spend much time on select because it's quite simpler, but I'll be able to do much later on when using the handler, the helpers, whereby you'll be. I'll show you once we have processed, once we combine this into a huge dataset with all the variables that we need, we'll be able to actually be able to do select more. But for now, I'll just show you how you select and how you drop. So suppose I wanted to like exclude some variables from my dataset, for instance. So the opposite of selecting, so of course dropping, and as it sounds, you basically negate, or rather like you leave out those particular variables from your data. For instance, if I wanted only maybe 3 variables, age and gender and PID, sorry, I wanted to drop the last 3 variables. What I'll do is I'll say maybe, let me call it data frame 2. I'm going to have many of these here, don't worry, but just keep track of what we are doing. So I'll call in, the first argument is the dataset that I'm using. Then I can create a vector containing the names of the variables I want to drop. But just before the vector, I put the minus sign indicating that I want to basically drop the names inside this particular vector concatenation. So if I do age, and gender, what this means that this particular dataset will not contain age and gender because I'll have dropped them. So this is the most simple part. So you realize I have all the variables, but I don't have the gender and age in it. So there's another way of selecting. So it's not. So this approach is basically naming the variable, like giving the selecting by giving the actual names of the variables in the dataset. But you can always also select by position. So for instance, I can always say, let me say selecting by position. So of course I have 12 variables. So of course, if I do names for the baseline data, so I'll get indexes. So this square brackets you see here. So it means that PID is position 1 in my dataset, time points position 2, 3, position 4, position 5, like that. So you can always select or drop variables based on their position. So for instance, if I wanted to select, say, variables in position, say 1, 2, and say 8. So what I'll do, I'll basically say select, then my baseline data, and then I'll either just, I can decide to have a vector, or I can just decide to type the positions explicitly, like that. So then position 1 is PID definitely, then 5, 6, 7, 8, 8 is gender, and 2 is time point. So if I do this, if I run this particular code, you realize that I have those particular variables. And you can do the same for deselecting. So just negate, put a negative sign, a prefix of a negative sign before the variables, and then you drop that particular variables. Okay, so as I said, use of helpers will basically make much sense later on. So I'll just skip that for now, and I'll demonstrate how that works. So that's basically how it is, selecting, or rather selecting or dropping variables from your data set. Okay, I'll move to the next verb that I'll say this one now is using a combination of any logical tests that you have in mind to particularly affect the number of observations. So if you look at the previous section, select affects the number of columns. For example, if you apply select to a data set, the number of observations remains the same, but the number of columns either will go down, or so definitely will go down, because you are either selecting a few, or you are dropping others. So I want you to note the difference, because this sometimes confuses between filtering and selecting. So for filtering, you basically want to subset your data based on some logical condition. For instance, in my data set, I have like age. So maybe I want a data set containing people who are between a certain age. That's a logical condition. Or I want a data set. I have a variable residential, so urban or rural. So I want those. I want to create a data frame for only those who reside in the urban areas, and I have a variable for hospitals. So maybe I want to have a data set which contains only volunteers or other research volunteers from hospital A, and for that instance. So those are logical conditions. And we are going to explore a few. For instance, I'm just going to do a few examples, but full-blown of some of this workflow will make more sense when I introduce you to the pipe operator, for instance. Okay, so yeah, so for example, if I wanted to, so if I look at the baseline data like that, yeah, so you'll get to see the nature of the variables and what the values and everything. But usually you can always just, if your data set is sizable enough, like mine here, you can always click and view the all of it and just make sure that you know the entries. Or you can always use the table variable, the table function. If you're not sure, what levels does your data contain? So for instance, I wanted to see the hospital, what are the possible values? So then I know I have 3 possible values. So I have level A hospital, level B hospital, and level C hospital, like that. So suppose now I wanted to maybe have a data frame for, say for instance, level A hospital. So I'll just say, I'll create an object, say level A, and assign that to, so the syntax for filter is the same. So the function is filter. You pass in the data set which you want to filter, for instance. Then you pass in now, the next is the logical condition that you want to apply. What do you want your rows to be subset by? So in this case, maybe I want my rows to be, I want my data to be sized based on the type of the hospital. So maybe I want only hospital A. Then that's what you do. So then just pass in the name of the hospital like that. And if I run this, I'll get a data frame here, which you can see has few observations, but the same number of variables. So, because I've actually taken part of it. So suppose I wanted to say I want hospital A, but who are male or female. So you can combine that. So can do so hospital A, say male or something like that. So then you add that particular logical to what you had already. So, and we normally use utilize the various logical operators to basically combine 2 logical conditions. So you can either use or you can use and based on what you really want. So for instance, if I wanted either hospital A or male, meaning either condition, whichever is satisfied, I get my data set. But if I wanted only those in hospital A, but they are male, so then I use and. So you have the logical and you have the logical or. So the logical or is usually a vertical in R, it's a vertical like bar like that. So then I'll just add to the condition and say what I need to do is I want where gender is male. So what will happen here is that I'll have even fewer number of observations because I've went further to actually decide that I don't want only level A, but I also want the gender male. Suppose I want to use something to do with maybe age. Suppose I wanted people who are maybe taller than, maybe height taller than 50 centimeter and maybe younger than say 10 months. So you can do that as well. So I can, let me call that age height, something like that. And I could say, assign this to the filter function, sorry. Then provide the data set. Then write in your condition. So what you are saying is that you want people who are less than, you want observations whose age is less than 10 months, or, so the logical or for R is just the vertical bar. So you want people whose age is less than, observation whose age is less than 10 months, or they are taller than, say 50 centimeters, so like that. So if you do that, you'll get a data frame age height, which is also less, with less number of observation. And if you try to quickly run the summary command on that particular data set, you realize that on the age, sorry, yeah, so because of the or, so it simply means, so you'll get, of course, observations whose age is greater than 10 months, but you realize that their height is, they are taller than 50 centimeters. So this just to get to understand that for when you use or, it simply means you, either of the condition is fine with you. So you're not really restricting. It's different from when I change this to something else. For example, if I change this to, when I change the logical or to say and, so then that really becomes a different thing, because now I'm narrowing down the condition. I want people who are, they must be, the observation must be 10 years or 10 months or younger, or not or, but, and they have to be taller than 50 centimeters. So if I do that, I'll get a much linear data set, and you realize that you won't get anyone who's, you won't get any observation that has an age which is greater than 10 months and so forth. So great. So I think for the filter, I'll stop there, because I know there are other things we'll do on filter, select, and everything, when we just get to understand what's the type of data for now. So I think, yeah, you'll be able to actually understand, like write more elaborate functions for manipulating this data set. Okay, so for the type conversion, I think this is pretty much easy. And if you've used R, I'm sure you've done it before. So for instance, if I look this function called class, not class, but let me say str for structure. So if I run str on my data set, just to get to understand the structure on my data set, just resize that and probably use this other one. The glimpse is from dplyr, so it works the same way with the str, but it gives a much better output like that. So you realize that you have your variable name and the data type here. So the PID is a character, time point is a character, date is a character, it's not a date, and yeah, so like that. So you can always convert a variable to from one form to another. So, and what you do is you use the as dot, this tags as dot. So if you want to convert a variable to a character, you just apply as dot character to it. As dot numeric, if you want to convert to a numeric vector, numeric data type, and so forth. I will also skip this for a later stage, so whereby we'll basically be able to convert all these variables from one state to another, in particularly the dates and everything, so that we have a proper date. So yes, so I will then move to renaming. So sometimes your variable names are not in the names that you want them to be, so you'll want to give them different names. So so that is here. So I'll just flip-flop that. Sorry. Yeah, and so we have a function rename from deployer. So we can use rename to actually rename, then you change the name of our variable. For instance, if I wanted to change same data set, yes, let me say, let me have baseline. So then I want to probably rename the first variable. So I want to rename the PID to something else. Maybe I want to something like something understandable like record ID, something like that. So what you do, the syntax is the same. So you just call the function rename, then of course your data set. So the syntax for renaming using the function rename is you start by defining your new name. Like for example, I want this to be called to be changed to record ID underscore ID. Then you equate to the old name. So this the old name is the name that is existing in the data set. So then it's PID like that. So if I run this, I will have altered the name of my first variable. So you can see it's now record ID. So you can do multiple. So you can do multiple this by just separating those with a comma. So suppose I wanted to rename the age variable to maybe age in month, something that it makes sense. So you can just say this is age in month is my new name, but I want to name that to something else like age. I want to rename age to age in months. Again, if I run this, of course, I expect that because I have altered the original data. I promised I won't do that, but yes, I just have to go back and do that. Then I'll learn from my mistake and try not to replace the. Okay, so yeah, I can maybe have it. Yeah, let me say this renamed or something like that. Perfect. Yeah, so then it means the data set that I'm renaming is the original one, but the resultant is actually assigned to this particular object. So I'll do that. Then I'll just say limbs on the new one, the baseline name data like that. So then you realize that the original variable, which was age, is now renamed to age in months. So you can also rename using some function called set names from data table package. So, and this one is quite different because you don't have to assign the results of the expression into an object. You just call the set names for set names, then you specify the data set that you want to particularly rename. That's the one. Then the syntax is the opposite of what we just talked. So you start with the old, and there's no using the equal sign. So it starts with old. The old name is say PID, and the new name is say record ID like that. What set names does, it will alter the structure, the names of the baseline data and assign it to the same, like, of course, it won't print anything. Sorry, was I supposed to do that? Same to that time, sorry. Okay, so if I open up baseline data, you realize that the first column has been renamed. So, and I didn't have to particularly assign to anything. So something to mention with the rename function, you can also rename with the position. So you don't have to particularly name. Say, for example, I could have just done this for this one. So because PID is position 1, I could have just changed this to 1, so and it will still work. So, so I'm saying rename the column in position 1 into record ID. So you don't have to. You also, so if you know the exact position of your column name, you can always also refer to it as with that position instead of specifically like typing it out. Okay, so I'll stop rename at that and say that you can also rename using select. So remember, we use select to to do what, to retain or to drop or retain variables. You can also use select, particularly to name a variable. So for instance, I could have done, but for select, you have to be very careful because it simply means that you have to select all the variables because, or maybe I should demonstrate. So rename using select. So what this does is that I'll select, use the baseline data. Then, so it also takes the same syntax. It's new equals to old. So for instance, in the baseline data, like that, suppose I want to revert back to my original name. So what I'll say is, so I'll say select, but use the syntax for naming. So I'll say select PID equals to record ID. So what this means is that while selecting these particular variables, change this record ID into PID. But if you stop at this, it simply means you'll only have one variable in this particular data set. And therefore, so this used very, very carefully when you're dealing with probably very few variables. But if that's the only thing you wanted to rename, you can always add this very useful function called everything. So it just means select PID, so select record ID as PID, but again, select everything else. So then I'll run that. And if I open rename select, I'll realize that now it's named PID and I have everything here. But if I hadn't included this particular function here, I will have ended up with one variable because that's what select does. So it actually executes the instruction of either selecting or dropping. So that's how you can use select to rename your variable. Okay, so I will now move to variable recording. So sometimes you want to have like, I mean, I didn't have that example here, but for instance, if you wanted to create, say, a factor from a variable, say, for example, if I look at the variable baseline data hospital, you realize that it's a character vector, but when you use table on this particular variable, we realize that it had 3 levels. So suppose you wanted to basically convert that into a factor. So a factor is a special character vector where we have like a numeric value stored together with the label of the variable in equation, whereby now you are able to actually, if there's some ordering into it, you can be able to order them, and usually it's very helpful when you are using it in maybe ggplot when you're plotting. It's usually very advisable to define your variables so that they are factors or they're just characters. And I will advise if you really mean them to be factors, you need to record them into factors. So how you record that into how you record a variable, or rather how you specifically do that is by using the function factor. So I'm just going to demonstrate right now. So I'll say, let me just still call it baseline recorded or something like that. Then I assign it to, you realize that the syntax for these particular functions are the same. So because you just call the function itself, then you start, the first argument is the data set, and basically for this one I think it's a little bit different, but when we get to work with the pipe operator, realize that it also behaves the same way. So for this one, we'll slightly do something else. So we'll just probably try to use the $sign to say maybe I want to create a variable called so baseline data, sorry, then maybe a new variable called hospital something categorical, like that. So then you assign this to factor. So what you are creating a factor out of is the particular character vector of your data set, which is basically the hospital. Then now you define the specific levels that are so the levels are basically the unique inputs in this particular variable, which are basically these ones. I can just copy this to save time and just paste it there and try to do something like this. And of course, separate them with a comma, like that, like that. So then you can go ahead and give them labels. So labels, these are the visual, I mean, what you'll want to see when that data is printed. So maybe you can go ahead and say, instead of having the whole level, I just want to have A, then B, and particularly C. So and you can always, type the help function. So if I do that, and I try to look at the class of the baseline data, particularly the hospital category, you realize that this is a factor. And if I do maybe summary on it, I don't have to type that. So let me just up one step, then just. Yep. So it behaves as if I've called a table function on it, but usually, actually, I want to, if you compare that with the when I will have done summary for the initial variable, you note the difference, and yeah, probably that tells you how relevant the recording, rather changing explicitly a variable into a factor. So then you can always use the help function. So just type a question mark and the function that you want to get help for. So this particularly gives you the specifics of the argument and even the explanation and what you need to do. So this can be done for every other function you've used. You can do the same for select, even for filter. So just to understand how to use the filter and how to use the select. So any function that you are using and you don't really know how it goes with it, so you can always get help by just typing the question mark, then the function itself. Then you will get a little bit of explanation and how you can use that particular function. Okay, so I want to move to the last verb, but I'm aware of the case when, but we'll basically be able to like use it later on. But for now, let's just look at the next verb, which is mutate. So mutate is basically used to create creating variables. So mutate is I don't want to say it's the opposite of select, but it more like does what the opposite of what select does. It affects the number of columns, but in the sense that you are adding another one to it. So just remember that select and the mutate affects the number of columns, but filter affects the number of rows in the sense that you have less rows. Okay, so so mutate, similar syntax. So for example, I mean, these are very basic example, but I mean, let's do it and probably do another advanced one later on. But yeah, so suppose I wanted to, from my data set, baseline data, this one here, suppose I wanted to say create some variable maybe that utilizes the maybe the weight and height, rather even the age, and so maybe I wanted to convert this age in months into something like in days or something like that. So by multiplying by a factor. So what I'll do is I use mutate. So, and the syntax for mutate is same. So we do mutate. So I'll say baseline mute. So I'm just going through this quickly because I know we are going to do a lot more of them down there, because I mean, it makes more sense combining some of these operations. And now I just want to get, I want you to get the sense of what really happens and how to use them. So mutate, just call the function mutate, and give it the first argument is the data set that you're going to use to do the particular mutation. Then I said the syntax is key value pair. So key meaning what's the name of the variable you want to create, and value pair meaning what is the computation, what's the instruction. So, and on the value part, anything can go. You can do an if else, you can do a whole lot of things, so long as whatever you're doing is a vectorized operation, meaning it can loop over rows and try to create a single value for each of the rows it actually loops through. So for this instance, I want to create a variable called age in days. So age in days, the value for age in days is, I'm using the existing value, which is age, then I'm multiplying by some constant, which is, say, let me say 30.4. So if I do that, I'll get this mutate, baseline mute that has been mutated. Then I'll find another variable at the end here. So this the automatically, when you mutate, when you create a variable, it gets pushed to the end of the data frame. So it comes as the last variable. So the more the variables you create always comes at the end of the last column. So it gets appended there. But that behavior, you can change it. You can look through the help for mutate and see how you can always specifically instruct where the variable comes. But I find this behavior, the default behavior, I mean, very, very helpful. So, yeah, so you can see we have a new variable, which is just basically this age times constant to make it age in days. So the value for your mutate or whatever variable you're creating depends on the instruction. What do you want to create? For instance, we're going to do another example, a more complex one. Then at least you'll be able to understand specifically really what the power of some of the things you can do with the mutate. And yeah, so plus, I mean, you could even replace, I mean, you can use mutate to replace the value of the existing variable. And I think that's something we can look at next. So at this stage, I don't want to go to merging yet, because I'll just quickly introduce you to pipe operator so that we stop the suffering and be able to see the flow correctly. So, so if you have never used the tidyverse, there's this symbol. So it's percentage rather than sign percentage. So we call it a pipe operator. So the pipe operator, its major function, the way it works is actually help you have like a complete, like a logical flow of operations. For instance, I want to demonstrate something. So suppose I'm going to remove everything in the console and start something else. Sorry. So I'll just read the data afresh. Like that. So then, yeah, so suppose I wanted to do something like this. So suppose I wanted to filter my data set, or rather select and filter at the same time. So suppose I wanted to start with maybe hospital A. Suppose I wanted, the end goal is I want how many variables I want from the baseline, from the baseline data. Add baseline. I want, say, PID, date, and say height and age. But so I want those variables, and I want from the same hospital, but I want those who are maybe less than 6 months or something, or less than 10 months, or taller than 60 centimeters. So in that case, you will have to have, you'll go through 2 steps because now you are talking about selecting and filtering. Okay, so depending on where you want to start, you eventually have 2 objects in your data, in your working environment. So you start by the first object. So let me start with selecting. So I'll say, yes, definitely I'm selecting from baseline data. So I want the PID, I want the weight, and I want height, then I want the age. So that's the first object that you'll have, okay? Because I'm going to also apply a filtering. So it's hospital A, PID, weight, height, and age, but I want people, or rather I want observation which are younger than a certain age or taller than a certain height. So this is the first object you'll do, like that. Then now your final object, which would be, say, host A, taller, say taller than 60 centimeters. You'll utilize your first object, because I mean this is what contains your particular variables of interest. Then your filter function will be applied on hospital A, because that's the variable that has the specific that's the object that has the specific variables of interest. So then now you type in your logic. So the logic is, I want these people to be from this observation to be from hospital A, for instance, and they have to be maybe taller than let me say height. They have to be taller than, say, 60 centimeters. So what I'm trying to, did I do something wrong? Sorry. Yeah, I think I mistyped the name of the hospital. Just go and yep. Sometimes, yeah, that happens. Oh yeah, I didn't select the hospital. So yep, that can happen. So like that. Yep, so now I have my final data, which is here, hospital A, but individuals who are taller than 60 centimeters, like that. So this operation, you can basically use the pipe operator to do it on a single flow. So for instance, instead of writing those 2 lines and assigning it to 2 different objects, I can achieve the same by just getting the final object that I wanted. Let me call it B, but through using the pipe operator. So what you do with the pipe operator, you start with the original data that you are dealing with, so which is baseline data. Then you apply the pipe operator. So what the pipe operator does, it tells the next function, which is select. Okay. So then you want to select, you can start with the filter, you can start with select. But the idea here is to just understand what the pipe operator does. So the pipe operator just tells select that whatever you are using as your input data comes from this particular object. So then you can go ahead and select your variables. I want the PID. So the good thing with pipe operator, again, you realize when you start typing the variable, it suggests for you the existing variables in the dataset. So it makes your work easier. Then age and hospital. So you cannot you cannot make the mistake of mistyping a variable because it suggests for you. Then you add another pipe operator. Then apply your filter. So what again, the second pipe operator, what it helps is telling the filter function that whatever data you are filtering has already gone through this particular step. So it simply takes the previous output as the input of the function you're writing next. So for instance, it takes baseline data as the input for select, and it will take the whole of this already done, like I'll say this is hospital A. At this point, we are at hospital A. Then it uses that as an input for filter. So then you can go ahead and filter. You put in your condition for filter. So you say you want the hospital to be A, but taller than maybe 60 centimeters. So if you do that, you end up with this, particularly the same results, but you just did that by just getting one object. So having known that, I want us to do a few things from what we've just covered, but now applying the filter, applying the pipe operator before we do data merging and all those. So now you can actually use all of the verbs and at the same time here. So for instance, now I want to actually try to change a few of this particular. Now I want to prepare now this data set for my final, how I want it to be. So for instance, the date, you can see it's a character. I want it to be a date format. Probably I am not happy with the names the way they are, because I'm going to combine this data to another data set which has similar names. So probably I would want to change the names to have some annotation to which time point do this variable belong to. So maybe adding a suffix, maybe age underscore maybe M0, meaning baseline, or B or BS or something like that. And probably say I'm not happy with the weight and height, the way they are named. I can always do that in a single workflow. So for instance, let's just make those changes. So then at this point, I can always, the result of my workflow, I can always assign it to the original data. So meaning now, whatever I'm doing using the pipe operator workflow, the resultant effect is applied to my original data. Then at that point in time, I am basically good to go. So the first thing I want to do is maybe convert the date to a proper date format. So there's the package lubricate. I hope I did load it, but if I did not, I'll just go up there and check. Yeah, it's loaded. So I want to change this particular, maybe, let me just do this, baseline final, so that we don't have to go back reading the data. So I want to create a final baseline data set, which bears what maybe you have in mind. So for instance, I'll start with the, maybe converting the hospital variable into a factor, for instance, or I want to do the date variable into a proper date. So I'll just do mutate at that point. Then the value pair, you remember. So what I'm affecting is the date. So what I want the date to be, I want it to be a proper date. So, and you can see the weights, what the structure is basically this date, month, and year. So you can use the function date, month, year from lubricate and basically input date. So what this will do, it will alter the structure of the date by converting it from a character into a date. And you can go ahead and separate, do several mutate within the same workflow, but separating with a comma. So for instance, you remember the age in days. So I can decide to do that here. So then I want age in days, but this time around I'm creating a new variable. So then I can say that is equivalent to taking age multiplying by basically 30.4. You can go ahead and do something else. For instance, Yeah, I can create BMI, for instance. Yeah, is it weight over height squared? Not too. Yeah, so then yeah, so BMI, I think yeah, it's weight, I believe, over height squared, if I'm not confusing. So then you can write that particular function there. So then it's a mathematical whatever. It's a mathematical like expression. So, and if you ever used R, you'll realize that, I mean, this stands for like division. This stands for like raising to a power, or you can explicitly say height times height. But yeah, I'm happy with using this particular one. So then if you run that, you have base fine, and if you go to the end here, you realize I think I might have this is not cool. I believe this yep. I think it's the other way around, if I'm not wrong. Oh my, this is embarrassing. Okay, so then you have those variables, I mean, at the end here. So then you can go ahead and even apply a filter or replace, for instance, if I didn't want, so I just want to take an example of, say, maybe, say I want to take, I don't want the gender to be containing male and female. I want it to have maybe M and F. So for whatever reason, so you can always use mutate with another function. For instance, it's replace. You can say mutate replace. What you're replacing is gender, and whatever you're replacing is the condition. You can say whenever gender is male, you can always replace that with M like that, and you can do the same for female. So what I'm trying to say is that you can write a whole flow of this kind of arrays of data manipulation tasks, either filter or select, and all those in the same workflow, without necessarily having to create several objects by using the pipe operator. So at this stage, I want to change the names of I want to add, maybe I want to annotate the names, the variable names, by adding a suffix to these particular variables by saying maybe I want hospital underscore something, I want HP underscore, so that I can be able to annotate. But before that, I had this in mind. I can also go ahead. You can either continue with the same mutate, or you can create another mutate, but let me just continue with the same one. So I had this particular, quickly looked up through the internet. I think it's the hemoglobin like categorization of anemic status being mild, moderate, severe, and normal based on the levels of hemoglobin. So you can basically also create such a variable in your data set. So I'll just pick this instruction from here, then just place it down here for our reference, and just show you how you can create a composite variable like that. So using a mutate in conjunction with the case when. So case when is like if else, but are more easy to read and use. So I'll just say maybe anemic status or something like that. Then so that's the variable. That's the pair, and the value is a function of case when. So case when, inside case when. So what you do inside this particular function is to define your rules and use a tilde operator to actually assign it to a given annotation. So what I'll say is that I have a variable called HP. This is hemoglobin. I'll say to save time, I'm just going to copy this and paste it here, sorry. But at least you'll see the essence, but I'm going to change this particular one. So to instead of having HGO, I'm going to have HB because that's the variable name for hemoglobin. So what this means that when hemoglobin is greater than 10 and less than or equal to that, then you use a tilde operator to actually tie it to a given value. And same to that, same to that, same to that. So what this means is that you'll have like you're testing several if-else condition, logical conditions, but what you're actually creating is an anemic status from this particular variable called hemoglobin. So I'm going to run this code here. And if I open this particular data set of mine here, you realize that now I have a variable called anemic, so to signify anemic status, and you can go ahead and convert that into maybe a factor or something. So I want to rename all the columns to something that I'll use later on for merging with the follow-up data. So yeah, so what I want to do is I want to add a prefix to the columns to maybe signify the time point, say M0 or baseline for, yeah, or yeah. So you can do that using the function rename all. So what I'll do now, I'm going to go ahead and take the baseline final, this data set here, the one that I'm creating. This time around, I'm going to alter it. So direct, I'm not going to create a new one. Then you can always say, you can rename specific variables. So I want to rename all variables except the PID. So what name at means that there's a very powerful function called across. You can look it up. Maybe yeah. We might not be able to cover it here, but it's actually the reason, and it replaces what I'm using here, the name at. But I think maybe starting at this point is not really bad. So what I'm just saying here is that I want to rename the variables of my data set. And the vars function is basically trying to explicitly say what variables I'm renaming. But in this case, in this sense, I'm using the similar technique that we used under select above, that you are excluding a variable from that particular operation. So I'm excluding the PID from getting renamed. Else I'm renaming everything else. So then from there you can define an arbitrary function and say, whatever I want to do is to paste. So I'm pasting the column name. So when you say dot, simply means the column name and whatever you want to append to it. So I'm pasting that, and I want to append it to maybe month 0. So meaning maybe enrollment, and maybe I will separate that with an underscore like that. When I do that, I'll get my baseline final, each variable having like an underscore M0 like that. So meaning this, that's I'm trying to explicitly have a meaningful annotation to my variables, meaning trying to attach them to a time point that they were collected. So this is going to be useful when you'll be merging, and probably you don't want to end up with the variables that are not unique across and have a very dirty data set, which is basically not what you want to end up with. So having said that, I want to quickly move to joining the data. So joining is basically combining various data sets together. So, and there are several joining functions. We have the left join, we have the right join. I'm going to do an example each, but I'm going to use 2 data sets. So I'm now going to start utilizing this discharge data, for instance. So the discharge data contains data discharge information for the same observation in the baseline. So for instance, if I wanted to have now I wanted to combine the discharge and the baseline data because obviously I will want my data set to be like containing all the variables in one flat file. So you can utilize left join, and we are going to explain. I'm going to explain what each of the joins means. So let's start with the left join. So left join basically, when the syntax is you are doing left join A to B like that, and of course you are going to supply another function called by. So left join. So when you're left joining a data set A to B by some unique identifier to both, you're simply adding the columns from B to A for which there is a match. So for instance, I want to left join baseline and a discharge. So what this will do, I'm going to use a pipe operator. So I'm going to say I'm starting with the baseline data. Then I'm going to left join to discharge data. And my unique identifier, or rather the connecting column in both of the data sets, the PID, like that. So I'll end up with baseline discharge. And you realize that the number of observations have increased and the number of variables have increased. And for obvious reasons that like we've used the semi-join, you realize that now this is where you start questioning your data. Like I have information for discharge, but I don't have the same information. I have information for some patients for discharge, but they are not in my enrollment list. Then what went wrong? So that's where now you start particularly questioning your data and trying to ask questions. And was it a data entry error? Was it, where am I having this? And yeah. So what this has done is that I have combined. I have added columns from discharge data to the baseline data for which there's a match. And if there's no match, if there are variables, if there are observations in the discharge data that have no match in the baseline, you realize that we have. Let me just open it here. Just scroll down. Yeah, so you'll have so many NA, and I think I might have used the wrong data set because now I'm having to deal with the time point.y and so forth. So I should have used the final data set, this one here, the one that I named. So now you see the significance of doing that. So then now I have a more linear and a more like better data set like that. So suppose I wanted to find out, so obviously the left join, you can do the same thing, the right join, and I believe if in the essence of time, I'll just direct you to that. Just look at the help of right join and you'll realize that it does almost a similar thing to, not as similar, but I think more like of a different arrangement of your A and B, but you realize that the logic is the same. I'm just going to look at the full join, not the full join, but the semi-join for now. So semi-join. So for semi-join, so there are two types of joins that you use to merge data. So we have this left join, right join, the full join. So those ones are usually called mutating joins because they alter the dimension of your data set. For instance, if you had, for example, I had 15 of variables here, but when I did a left join, I ended up with 22 variables because now I have brought in the discharge data. Okay, so that's why they are called mutating joins. So we have this other group of joins which we call the filtering joins. So the filtering joins in the sense that they don't really affect the number of variables in the data set, but they actually affect the number of observations. So for instance, I want to check something very critical here. So how many of my how many of my observation in the baseline data have a match in the discharge. So that's what you can achieve using semi-join. So what I'll do is, let me call it, I'm not running out of names. So then I'll start with the baseline data. So when I say semi-join, when I say semi-join to discharge data, what I'm querying here is of my 303 observations with 12 variables, how many do I have? How many of these are basically in, PID? How many of these are basically in the discharge? So you can see there are only 2029. So what semi-join does, it returns the observation on the left, or from the left-hand side dataset, which is the baseline, which have a match in the right-hand side dataset, which is the discharge. So this is what it has done. So 2029 observation have discharge information. So meaning out of the discharge, I think that's incorrect. Maybe what might be happening? Yeah, I believe that this might be the problem of simulation, because now you end up getting something that's not really make a lot of sense to you. So I think I will try to see if I have duplicates, and that's something we're going to check again. And I'll go ahead and maybe do an antigen. So an antigen is basically the opposite of, not opposite, but it does a similar thing, but more of answering a different equation. So for instance, if I wanted to find out how many observations in my baseline data that do not have a match in the discharge data, that's what antigen will do for me. So then I'll maybe call it different 2. And say baseline data, I should have used, okay, baseline data, then I'll do anti-join that, and do that with the discharge data, and use the PID as the, like that. So then I end up with 974. So simply means I have a deficit of 974. So that's how you can use the semi-join and the antigen to basically, if you have 2 sets of data sets and you expect maybe both to be having some observation or rather similar observation, then you can always try to check and see what you're missing, or rather what if you eventually do a match, what are you actually going to like have matches for, you're going to miss matches for. I think my data simulation process did not go well, and I'm ending up with some scenarios which you not expect in real research data. Yeah. So binding rows basically what joins do, and we have. I'll also direct you to go and look at the full join, because it does something that you realize maybe left join and right join does not do. So you can just look at the help of full join and right join and try and see what that does. So you realize that when you are doing the joins, the mutating joins, we were adding columns to an existing data set. So you can also add rows to an existing data set. So for instance, I can add rows from the baseline. Now that I have, of course, time point, I can add rows from the baseline data set to discharge, or discharge to baseline. So again, there are 2 functions I normally use. Mostly I use the deploy bind rows, and there's another function from this package.
Let me allow me to.
So we have not utilized the follow-up data. So the follow-up data is a task like time point, visit 1, visit 2, and all that. I think what I want to do is I want to combine baseline, discharge, and follow-up into one flat file. which is tidy data. So you have one observation, an observation like a row represents an observation and a column represents a variable. But if you look at this, we have like this one appearing twice. So that's the nature of the long format, and basically this is not what you want in your normal. So so I'm just going to start. So I'm going to basically, first of all, visit one. I'll just extract that from follow-up data. So in filter the visit, so time point basically is visit one. And what I'm going to do with this one, I'm going to convert it into wide format. It's in the long format currently. So what that means, I'm going to take use the function pivot wider, and I'm going to so what pivot wider does, it takes two columns and spreads it into one column representing the number of variables, the variable names, and the other one represent the values. So my variables will come from the variable column. So I'll just say variable, and my values for those particular variables will come from the measure variable. Then I'll end up with the visit one with this, which is basically a long format, and I will go ahead and rename this so that I can be able to merge it back without any. So similar like what I did above, then I'll go ahead and do. So I'm going to put a suffix at the end of it, signifying that this is a variable that comes from visit one, and do an underscore like that. Perfect. So if I do this, we'll have this data set, which has something like that. So because maybe I could, because I have similar structure, and because of the time, I'm just going to copy paste this and just change the time point. So for visit two, I'll have the same because they're the same. So then I just change this. This is a bad practice. Pasting should basically type, but yeah. Perfect. So when I do this, I'll have visit three. I'll have these three data sets which contain my follow-up data, visit 1, 2, and 3, respectively. And now I want to match this to my discharge. So combine the data set, combine baseline, discharge, and the follow-up data. Okay, so then I'll say this is my final data set. Assign it to, so I'll use the baseline, the final baseline that I created, that. So instead of writing there several, because I have how many? I have 4 data sets to left join. So there's a function, a very nice function called reduce from the R package. So what reduce does is it passes you give it a list, then based on the function that you want to use to aggregate that data, rather to apply to the list of the data frames you have. It can either do a row bind, it can do a left join, and all those. So then in this case, I have the baseline final data set, and I have the discharge data, and I have also the visit 1, I have visit 2, and I have visit 3, like that. So what I want to do with these data sets, I want to do a left join because I want, or left or full join. So, but for me, I want to do a left join because I just want to assume that baseline final data has all the IDs that I need. So then I'll just supply that function here. and definitely give it whatever column you want it to use in left joining, so which is the PID. So when I run this, I end up with the final data frame, which contains all variables, and you can see it's more like what I will have wanted. A single observation is a single row is an observation, and a column is a unique variable, in the sense that now if you do table the final data, then maybe time point. Yep. So yeah. So I think something might have happened somewhere here. Yeah. You see now the disadvantage of pasting. So yeah, then can repeat that. Okay. So the idea is I have a data frame, which is a flat file, whereby I have a row is an observation and a column is my variable. And the variables have been annotated based on when they were collected, if it's during admission, discharge, or during visit 1, visit 2, and so forth. So I think I didn't cover, like, I would say I've covered Lucy, say 60%, 65 or 70. So to be just what I'm going to do, I'll promise I'm going to write like a tutorial out of this in a remark, and then I will send to the participant who joined this session in less than 2 weeks time, so that you can get a full view of what I really wanted to do with the data manipulation and the management part of this particular talk. Thank you, Lucy.
Okay, thank you so much, Chris, for the wonderful and insightful tutorial. So we have some questions for you. So let me start. Okay. So, so due to time, we will ask one more last question. The rest of the questions, they will be answered via the Slido. So please, because you have the link and you have the code shared, please do log in, and you see all the questions will have been answered, sorry, by Chris. So Chris, one more question. What is the difference between rename and rename_at?
Okay, that's a very good question. So rename is a general syntax for changing the name of a variable from one version to another, and for it you explicitly type based on the syntax that I showed, like the new and old. So rename_at is more of a conditional. So you are renaming at a specific point on your data set. So for instance, you had like 1,000 variables, okay? And there are some variables which, for instance, take maybe a certain structure. Maybe they start with some pattern or something like that. So if those particular variables are maybe say 150, so what rename_at helps you is to specifically navigate through up to that particular point of interest that you want to specify your name and basically affect that. But I would say if you look at it intuitively, there's no big difference, because I can basically I can say rename_at maybe age, then say something like that, something else. But ideally, when it comes to larger scale usage, there's a very big difference.
Okay, thank you so much. I hope the 2 questions have been answered. Chris will answer all the questions in the Slido. During the talk, I was sharing with you the link and the code. Please do log in, and you will see all the questions will have been answered as the day proceed.